Deep in the cosmic dark, stellar corpses wander with unimaginable power. These are neutron stars, the universe's ultimate cosmic zombies, the incredibly dense remnants of stars that have died in violent supernova. But the most mysterious of all are the ones hiding in the farthest reaches of space, billions of light years from Earth. By the end of this journey, you will know 28 astonishing facts about these distant powerhouses, secrets that challenge our understanding of physics itself. We will uncover how they act as cosmic lighthouses from the dawn of time, and what their extreme gravity can tell us about the fabric of reality. What single question about the universe feels most urgent to you right now? Billions of light years is a distance that defies human comprehension. When we call a neutron star distant, we are not just talking about a faraway point in space, we are talking about a message from a different era. The light reaching our telescopes today from such an object began its journey when the universe was young, perhaps only a third or even a quarter of its current age. This is the principle of look-back time. You are not seeing the star as it is now, but as it was billions of years in the past. It is a cosmic fossil, a snapshot of a younger, more violent universe. Observing these distant objects is the closest we can get to time travel, allowing us to study the conditions and the behavior of matter in the early cosmos. The challenge, of course, is staggering. Detecting the faint, precise signal of a spinning neutron star from across such a vast gulf of space and time is like trying to read the serial number on a coin from the surface of the moon. It requires telescopes of incredible sensitivity and sophisticated data analysis techniques to separate that one whisper of information from the cosmic background noise. Every single data point is a triumph of technology and theory, a fragile thread of light connecting us directly to the universe's infancy. That faint signal is a direct inheritance from one of the universe's first great catastrophes. These distant neutron stars were born in the depths of the very first generation of stars, colossal giants that lived fast and died violently. When one of these primordial behemoths, hundreds of times more massive than our own sun, exhausted its nuclear fuel, its core collapsed in a fraction of a second. The resulting supernova explosion was not just a star's death, it was a foundational event for the cosmos. These were among the earliest cosmic explosions, and their violence was essential. They blasted space with the first heavy elements forged in their hearts, seeding the sterile hydrogen and helium-filled void with the raw materials for everything to come, including the planets and life itself. But these ancient supernovae were fundamentally different from the ones we observe today. The first stars were made of almost pure hydrogen and helium, with none of the heavier elements that help modern stars regulate their deaths. This pristine composition meant their final moments could trigger far more exotic and energetic events. Some likely succumbed to a phenomenon called pair instability, where the core becomes so hot it spontaneously creates matter and antimatter pairs, leading to a runaway reaction that completely obliterates the star, leaving nothing behind, not even a black hole. Others might have exploded as hypernova, titanic blasts that could be hundreds of times more energetic than a typical supernova, powered by the rapid spin of a collapsing core. It was from the absolute extreme end of these primordial cataclysms that the most distant neutron stars were forged, cast out into the expanding universe as relics of its most chaotic and creative era. Catching that faint echo from the cosmic dawn demands instruments of almost unimaginable power. Our most powerful eyes on the universe are not single telescopes but a fleet of specialized observatories, each designed to see the cosmos in a different light. The legendary Hubble Space Telescope captures the universe in stunning visible detail, while its revolutionary successor, the James Webb Space Telescope, peers deep into the infrared, seeing through veils of dust to observe the earliest galaxies. But to hunt the most distant neutron stars, astronomers often turn to an even more specialized hunter, the Chandra X-ray Observatory. Why X-rays? The answer lies in the extreme nature of these stellar corpses. A neutron star's surface is a furnace of intense heat and unimaginable magnetic fields, trillions of times stronger than Earth's. As these incredibly dense objects spin, sometimes hundreds of times per second, their powerful magnetic fields can whip charged particles to near light speed. This violent process generates tremendous amounts of high-energy X-ray light, a brilliant beacon that cuts straight through the interstellar gas and dust that would block ordinary visible starlight. It is like using a penetrating medical X-ray to see the bones of the universe, rather than a simple camera that only sees its skin. Chandra acts as our cosmic X-ray vision, isolating these precise, energetic signals from the vast, dark background of deep space. Each detection is a monumental achievement, a single point of high-energy light that represents the final, enduring scream of a star that died when the universe was young. So what happens when we finally manage to pinpoint one of these distant, spinning relics? The answer reveals a reality even stranger than we anticipated. The current champion of cosmic distance bears the name UHC-1. Discovered through the combined power of the Chandra X-ray Observatory and the James Webb Space Telescope, this object lies at a staggering redshift of approximately 10.1. To translate that into time, the light we are detecting from UHC-1 began its journey to us when the universe was only about 480 million years old, a mere 3% of its current age. We are witnessing its story from an era when the first galaxies were still actively assembling themselves. What revealed this stellar ghost was not a steady radio pulse, but the brilliant, high-energy flash of an X-ray binary in the act of feeding. This specific signature told astronomers they were seeing a neutron star locked in a gravitational dance with a companion star, violently siphoning material from it and heating that matter to temperatures so extreme it glowed in X-rays. Think of it as catching the brief, brilliant flare of a cosmic predator in the deep dark, a single, luminous event that allowed its position to be pinpointed across an inconceivable void. The light from UHC-1 has been traveling for over 13 billion years to reach our telescopes, meaning we are observing a cataclysmic event that occurred before Earth even existed. This single point of data is a fossilized heartbeat from the universe's childhood. The sheer density of a neutron star is a physical reality that defies all intuition. Picture a mountain, one of Earth's great peaks, with all its immense mass of rock and ice. Now imagine crushing that entire mountain down into a single, perfect sugar cube. That is the density of matter inside a neutron star, where a single teaspoonful would weigh billions of tons here on Earth. This staggering compactness is a universal rule for these objects, a direct result of their violent birth. Yet for the distant ones like UHC-1, this fact carries an even deeper implication. It has maintained this impossible state of matter for over 13 billion years, resisting the relentless pull of its own gravity that should, by all rights, have crushed it into a black hole long ago. That enduring stability is a profound mystery in itself, a testament to the strange physics at play within its core. This incredible density creates a gravitational field almost beyond comprehension. The surface gravity is hundreds of billions of times stronger than the pull you feel standing on Earth. If you were to somehow attempt a landing on its surface, your body would be compressed into a thin film of atoms, thinner than a sheet of paper, in a fraction of a microsecond. This gravity is so intense that it doesn't just pull on matter, it actively warps the very fabric of space and time around the star, creating a deep, invisible well in the cosmos. Light itself must fight to climb out of this gravitational pit, losing energy in the process, a phenomenon we observe as gravitational redshift. This warping effect is our key to understanding how these distant objects interact with their surroundings, bending the light from galaxies behind them and acting as cosmic magnifying glasses. Their gravity is not just a force, it is a sculptor of reality. This profound warping of space-time does more than just trap light, it can also magnify it. The immense gravity of an entire galaxy, or even a cluster of galaxies, can act as a natural cosmic telescope. When such a massive object sits directly between our observatories and a far more distant neutron star, its gravitational field bends and focuses the star's faint light, a phenomenon known as gravitational lensing. It is as if the universe itself provides a helping hand, placing a magnifying glass of unimaginable scale in front of our most elusive targets. This lensing effect can amplify the neutron star's signal, making a faint, unreachable whisper suddenly loud and clear enough for us to study in unprecedented detail. In one remarkable observation, astronomers used a foreground galaxy cluster to study a lensed neutron star. The lensing did more than just make the star brighter. It created multiple images of the same object, smeared into faint arcs of light around the cluster. By carefully analyzing the precise shape and brightness of these arcs, scientists could perform a kind of cosmic weigh-in. They calculated the mass of the lensing cluster itself, and more importantly, they confirmed key properties of the distant neutron star, such as its own intense mass and compact size, data that would have been utterly impossible to gather without this natural telescope. This single observation provided a direct test of our theories about how matter behaves under such extreme conditions, all thanks to a perfectly aligned gravity well in the depths of space. That blistering heat is a direct remnant of the star's violent birth. When a stellar core collapses into a neutron star, the energy released is so immense that the newborn object's surface temperature can soar beyond 1 million degrees Celsius. To put that in perspective, the surface of our own sun is a relatively cool 5,500 degrees. This is a furnace of almost pure creation, a thermal echo of the supernova blast that forged it. Over billions of years, these distant stellar cinders slowly radiate their heat away into the void, cooling down. But even after all this time, many still retain a surface temperature of hundreds of thousands of degrees, a faint, enduring warmth from the early universe. This incredible heat is only half the story of their power. The other half lies in an invisible, unimaginable force. The magnetic fields surrounding these objects are not just strong, they are fundamentally world-altering. They can be 1 trillion times more powerful than Earth's protective magnetic shield. At this intensity, the field itself becomes a tangible entity. It warps the very atoms on the star's surface, stretching them into long, needle-like shapes. In the void just above the surface, the magnetic field is so potent it can tear apart molecules and create a bizarre form of matter unlike anything we can replicate on Earth. The most extreme of these are known as magnetars, neutron stars where the magnetic field is amplified to even more ludicrous levels. This magnetic prison creates immense stress on the star's solid crust, a crust that is harder than diamond. When the strain becomes too great, the crust suddenly cracks and shifts in a starquake, a seismic event of cosmic proportions. The energy released in such a fracture is staggering. In a fraction of a second, a magnetar can unleash more energy than our sun will emit over 100,000 years. This energy erupts as a colossal flare of gamma rays and X-rays, a flash so brilliant it can momentarily outshine every star in its host galaxy. It is one of these very flares, a cosmic scream of magnetic energy, that often allows us to detect a distant magnetar in the first place, its momentary fury lighting up our telescopes from across the cosmos. That magnetic fury often channels itself into a perfectly timed cosmic beacon. Many distant neutron stars are born spinning at dizzying speeds, some rotating hundreds of times every single second. As they whip around, their powerful magnetic fields funnel intense beams of radiation, primarily radio waves and X-rays, out from their magnetic poles. If these poles are misaligned with the star's rotation axis, the beams sweep through space like the brilliant, focused rays from an interstellar lighthouse. We call these rapidly spinning, pulsing neutron stars pulsars. For us to detect one, a stroke of cosmic luck is required. The path of that sweeping beam must intersect directly with our line of sight here on Earth. Each time the beam flashes across our telescopes, we register a precise, rhythmic pulse. It is a fleeting alignment across billions of light years, a lighthouse keeper on a distant shore briefly turning their light in our direction. This regular ticking is more than just a signal. It is one of the most reliable clocks in the universe. Over time, the pulsar's spin gradually slows down as it radiates energy away into space. The rate of this slowdown is incredibly steady and predictable. By measuring the precise timing of these pulses from a distant pulsar and calculating how much its spin has decayed over billions of years, astronomers gain a unique tool. They can use this natural chronometer to measure the passage of time on a cosmic scale, testing the fundamental constancy of physical laws across the vast age of the universe. This slow, inevitable winding down is the steady heartbeat of a stellar corpse, a rhythm that has been ticking since the cosmos was young. Beneath that unbreakable iron crust lies a fluid stranger than any ocean. The interior of a neutron star is a realm of matter pushed to its absolute limit, a place where the very definitions of solid and liquid lose their meaning. We believe this cosmic onion possesses distinct layers, each with its own bizarre properties. The outermost surface is a crystalline crust of iron nuclei, packed into an unimaginably rigid lattice, a shell harder than diamond. Just beneath this solid skin, gravity's immense pressure crushes atoms themselves. Electrons are forced into atomic nuclei, merging with protons to form a sea of neutrons. This creates a superfluid, a substance that flows with absolutely zero friction. In this state, the neutrons can move in perfect, coordinated unison, creating quantum phenomena on a macroscopic scale. Deeper still, at the very heart of the star, the pressure may become so overwhelmingly intense that even the neutrons themselves begin to break down. Here, matter might transition into a soup of free quarks, the fundamental building blocks of all particles, or coalesce into exotic particles known as hyperons. This is a state of matter that cannot be created or sustained anywhere on Earth, not even in our most powerful particle colliders. Every distant neutron star we detect, especially the ancient ones like UHZ-1, acts as a remote laboratory. Its very existence, its mass, its cooling rate, and how it spins all provide critical clues. They help us constrain our theories about what is happening deep within that neutron soup. By studying these stellar relics, we are not just learning about dead stars. We are probing the fundamental behavior of nature's forces under conditions so extreme they haven't existed since the first moments of the Big Bang. These stellar powerhouses are the suspected source of two of the cosmos's most violent and fleeting mysteries. Fast radio bursts are among the most puzzling signals we detect, incredibly intense flashes of radio waves that last for mere milliseconds, yet in that instant they can release more energy than our sun does in 80 years. For years, their origin was a complete enigma, seeming to come from random points across the sky. Then, in a breakthrough observation, a fast radio burst was traced back to our own galactic neighborhood, originating from a known magnetar, a neutron star with a devastatingly powerful magnetic field. The theory solidified, suggesting that at least some of these cosmic screeches are generated during star quakes on distant magnetars, when their crusts rupture under magnetic stress and release a catastrophic pulse of energy that ripples across the universe. This connection turns every detected fast radio burst into a potential candidate, a fleeting, brilliant scream from a spinning stellar corpse in a galaxy far, far away. But if that represents a stellar tantrum, then the birth cry of a neutron star is something else entirely, a gamma-ray burst. These are the single most luminous events in the universe since the Big Bang itself, outshining entire galaxies for a few fleeting seconds. Some long-duration gamma-ray bursts are thought to be the signature of a particularly massive star collapsing not into a quiet neutron star, but into a hypernova, a supernova on steroids, which then gives birth to a newborn neutron star or even a black hole, all while firing a narrow, focused jet of material and radiation at nearly the speed of light. When one of these jets is pointed directly at Earth, we see the resulting flash as a gamma-ray burst. Observing these bursts at the edge of the observable universe from redshifts of 8 or 9 does more than just record an explosion. It directly probes the death of the very first stars. Each distant flash is a cosmic autopsy, telling us about the mass, the spin, and the final moments of a stellar giant that died when the cosmos was in its infancy. Our cosmic lighthouses are almost always invisible to our most powerful telescopes. We never actually see the distant neutron star itself as a single, distinct point of light. Instead, we are master detectives of the cosmos, piecing together its existence from the energetic clues it leaves behind. We might detect the rapid, clockwork pulse of X-rays from a spinning pulsar, a rhythm that could not come from any other object. We might catch the single, cataclysmic flash of a gamma-ray burst, the explosive signature of its violent birth. Or we might observe the steady, high-energy glow of an X-ray binary, the telltale sign of a neutron star relentlessly pulling matter from a companion. Each of these signals is a unique fingerprint, pointing unequivocally to the presence of one of these stellar corpses. But pulling that faint fingerprint from the background noise of the universe is a monumental task. The signal from a neutron star billions of light-years away must travel through the turbulent gas of its own host galaxy, then through the vast, diffuse intergalactic medium before finally hitting our detectors. It is like trying to hear a single, precise whisper in a roaring hurricane. To isolate that whisper, scientists employ incredibly sophisticated data analysis and complex computer modeling. They must carefully subtract the general light of the surrounding galaxy, account for interference from closer objects, and filter out the constant hiss of cosmic background radiation. Every confirmed detection is a triumph of inference and computation, a ghostly presence confirmed not by a direct image, but by the undeniable shadow it casts upon the data. This cosmic feeding frenzy often unfolds within a binary star system, a celestial partnership forged in the same stellar nursery. When one of the stars explodes as a supernova and leaves behind a neutron star, the gravitational balance of the system is thrown into chaos. The surviving companion star now finds itself locked in a deadly dance with a stellar corpse of unimaginable density, a partner whose gravity is so intense it can begin to literally devour the living star. The neutron star acts as a cosmic vampire, using its immense gravitational pull to strip away the outer layers of its companion. This stolen gas doesn't fall directly onto the neutron star's surface. Instead, it spirals inward, forming a vast, flat, and incredibly hot whirlpool of matter known as an accretion disk. Friction within this rapidly spinning disk heats the material to temperatures of millions of degrees, causing it to glow with an intense, persistent fire of X-ray radiation. This is the brilliant beacon we often detect from across the universe, the unmistakable sign of a neutron star in the act of feeding. The process does not end there. Over millions of years, this relentless consumption can completely strip the companion star of its mass, leaving behind a ghostly, stellar core. In some of the most extreme cases, the two objects spiral ever closer, ultimately merging in a cataclysmic collision. It is in the violent crucible of such a merger that the universe forges some of its heaviest and most precious elements. The intense energies and abundant neutrons present in these events are believed to be the primary cosmic factories for elements like gold, platinum, and uranium. The gold in a wedding ring or the platinum in a catalytic converter was likely born in the spectacular, destructive merger of two neutron stars billions of years ago, a final act of cosmic cannibalism that seeds the universe with the building blocks of worlds. This cosmic cannibalism can culminate in the universe's most spectacular forge, when two neutron stars in a distant binary system finally exhaust their orbital dance, spiraling inward over billions of years. They collide in an event of staggering violence known as a kilonova. This is far more than a simple explosion. It is a cosmic alchemist's crucible. The incredible density and intense neutron flux in the merging debris create the perfect conditions for rapid neutron capture, a process that forges the universe's heaviest elements in an instant. In the fiery aftermath of a single kilonova, enough gold, platinum, and other rare Earth elements can be synthesized to outweigh an entire planet. Every precious metal on Earth, from the gold in a crown to the platinum in a computer, was likely born in such a cataclysmic merger between two stellar corpses in the deep cosmic past. But the light from this elemental forge is only one part of the story. The collision itself is so violent, involving masses greater than our Sun moving at a significant fraction of light speed, that it literally shakes the fabric of the cosmos. It sends powerful ripples through spacetime itself, distortions we call gravitational waves. These are not rays of light, but literal waves in the geometry of reality, predicted by Einstein over a century ago. For the first time, with advanced observatories like LIGO and Virgo, we can now feel these tremors, detecting the gravitational wave signature of a distant neutron star merger, especially one from the early universe, would be like hearing the precise echo of that ancient crash. It would tell us not just that it happened, but the masses of the objects involved, their spins, and the nature of their final moments. Future space-based observatories will be sensitive enough to listen for these whispers from the cosmic dawn, providing a direct census of the ancient neutron star binary population and revealing the violent, creative processes that seeded our universe with the very elements that make our world and us possible. These distant collisions are more than just cosmic gold mines. They are precision tools for measuring the universe itself. When two neutron stars merge, they create a phenomenon astronomers call a standard siren. The name comes from the unique combination of signals the event produces. First, the collision sends out a very specific chirp of gravitational waves, ripples in spacetime. The properties of this gravitational wave signal allow scientists to calculate the absolute distance to the merger with remarkable accuracy. It is like hearing a siren and knowing exactly how far away it is just by the sound of its pitch and volume. Then there is the brilliant flash of light from the accompanying kilonova explosion. By analyzing the light from this fireball, specifically how its colors are stretched toward the red end of the spectrum, astronomers can determine the object's redshift, which tells them how much the universe has expanded since the light began its journey. Here is the crucial part. These two measurements, the distance from the gravitational waves and the redshift from the light, are completely independent. They do not rely on the same cosmic assumptions or a chain of other astronomical objects. By comparing them directly for a single event, scientists get two clear numbers. The redshift tells us how fast the galaxy containing the merger is moving away from us due to the expansion of space, and the gravitational waves tell us exactly how far away that galaxy is. When you know both the speed and the distance, you can calculate the rate of the universe's expansion, a number known as the Hubble constant. This is one of the most important numbers in all of cosmology, and for years, different methods of measuring it have produced conflicting results, creating a major tension in our understanding of physics. Each distant neutron star merger we detect as a standard siren provides a clean, direct measurement that helps resolve this tension, fine-tuning our knowledge of the cosmos's expansion and, by extension, its ultimate fate. Even with our powerful telescopes, some distant galaxies present a curious emptiness. This is the missing pulsar problem, a quiet puzzle at the heart of galactic evolution. Our best models of star formation and death predict that certain dense, ancient stellar clusters should be brilliant with the radio pulses of hundreds of neutron stars. Yet when we point our most sensitive instruments at them, we hear only silence. Where have all the pulsars gone? One compelling theory suggests they are not absent but simply veiled. In these crowded galactic cores, immense clouds of gas and dust could be smothering their radio beams, absorbing the precise ticks before they can ever escape their home galaxy. Another possibility is that the very environment that creates them also hastens their end. Perhaps intense gravitational interactions with neighboring stars either kick them out of the cluster entirely, sending them wandering into the intergalactic void, or disrupt the delicate alignment of their lighthouse beams, turning their rhythmic flash into a steady, undetectable glow. This missing population hints at a richer, more complex life cycle for these objects than we first imagined, one where a neutron star's visibility depends as much on its surroundings as on its own ferocious power. And this raises a profound question about their ultimate destiny. What is the final end for a stellar corpse that has already lasted for billions of years? The journey does not stop here. Over timescales that dwarf the current age of the universe, trillions upon trillions of years, an isolated neutron star will slowly, inexorably radiate away its remaining heat. Its furious spin will decay to a near halt, and its brilliant magnetic fields will fade into insignificance. It will become a cold, dark, solid sphere of pure neutron matter, a black dwarf drifting silently in the frozen blackness. This is one potential fate, a quiet fade into cosmic history, but for neutron stars living on the edge, another, more dramatic end awaits. Those that exist right at the theoretical mass limit, or those that slowly gain weight by accreting matter from a companion star, constantly flirt with disaster. If they cross a critical threshold, their own immense gravity will finally achieve what it has been threatening to do for eons. In a final, silent event that leaves no flash of light, the neutron star will overcome the last quantum forces supporting it. It will collapse inward, vanishing completely behind the absolute curtain of a black hole event horizon. In an instant, a cosmic anchor that has endured since the dawn of time simply winks out of observable existence, leaving behind only the gravity well it carved into the fabric of space. There is an ultimate cosmic horizon beyond which we cannot see. This is not a limitation of our telescopes, but a fundamental property of the universe itself. As we peer back toward the Big Bang, we eventually reach a time before the first stars or galaxies even formed, an era when the cosmos was a hot, dense fog of ionized gas. In this primordial plasma, light could not travel freely. It was constantly scattered by free electrons, making the entire universe opaque. This cosmic curtain only lifted when the universe cooled enough for atoms to form, a moment known as recombination. For neutron stars, this sets an absolute boundary. We will never observe one from before this time because their light, or any light, was trapped. The very first neutron stars to ever form are forever hidden behind this wall of glowing gas, their birth cries lost in the dawn of time. This cosmic horizon marks the edge of our observable universe, a final frontier set by the physics of creation itself. Even for the neutron stars we can see, their light carries the indelible mark of their immense journey. The expansion of the universe continuously stretches the fabric of space during the billions of years that light travels to reach us. This stretching affects the light itself, lengthening its wavelength in a process we call cosmological redshift. Think of it like drawing on a rubber band. As you stretch the band, the drawn line becomes longer and thinner. In the same way, the energetic light from a distant neutron star is systematically shifted toward the red and lower energy end of the spectrum. For the most extreme objects like UHZ-1, their high-energy X-ray and gamma-ray emissions are stretched so dramatically that by the time they reach our telescopes, they have been transformed. What began as a searing blast of gamma rays may arrive as a much tamer X-ray signal. This redshifting is a double-edged sword. On one hand, it is our most vital tool for measuring cosmic distances, a clear gauge of how much the universe has expanded. On the other, it acts like a cosmic veil, smothering the most energetic and revealing signals from these distant powerhouses. Detecting them requires instruments sensitive enough to find their stretched and faded whispers, forcing us to look for the ghost of a scream in the static of the cosmos. The James Webb Space Telescope is poised to listen for the cosmic echoes of ancient stellar collisions. While it cannot see the gravitational waves or the initial flash of a kilonova, its unparalleled infrared vision allows it to hunt for something just as telling: the afterglow. After two neutron stars merge and forge a universe of heavy elements, the expanding cloud of radioactive debris continues to glow, its light shifting into the infrared over weeks and months as it cools. For mergers that happened in the very first galaxies, that faint, warm glow is all that remains, stretched by cosmic expansion into the precise infrared wavelengths that the Webb telescope was designed to capture. Spotting this signature would be like finding the warm embers of a colossal, ancient fire, confirming that these cosmic forges were active when the universe was in its infancy. Each detection would provide a chemical fingerprint, revealing exactly which heavy elements were created in that specific cataclysm billions of years ago. This data would piece together the timeline of how the universe went from a sterile place of hydrogen and helium to one rich with the ingredients for planets and life. Every signal we gather from these distant stellar corpses is far more than simple data. It is a message in a bottle cast into the cosmic ocean billions of years ago. The rhythmic pulse of a pulsar is not just a tick of a clock, it is a story of a star's death spin. The faint X-ray glow of an accretion disk tells a tale of cosmic cannibalism. The silent, stretching redshift of the light itself carries the history of the universe's expansion. These signals have traveled for eons through the emptiness between galaxies to finally arrive at our telescopes. They bring us a direct report from the universe's violent youth, a narrative written in the language of extreme physics and titanic forces. We are the recipients of these ancient letters, and by reading them, we learn not only about the stars that died long ago, but about our own origins and the fundamental laws that shape all of reality. A silent symphony of gravitational waves constantly ripples through the cosmos, and soon we will have the ears to hear it. The Laser Interferometer Space Antenna, or LISA, is a future mission that will open this entirely new sense. Imagine 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers sensitive enough to detect a change in distance smaller than an atom. This colossal instrument will float in space, free from Earth's seismic noise, listening for the low-frequency hum of the universe. It will be tuned to hear the mergers of the most massive objects, including pairs of neutron stars spiraling together in slow motion for billions of years. While ground-based observatories catch the final high-pitched chirp of a merger, LISA will hear the entire cosmic duet. It could detect the gravitational waves from such a binary system years, even decades before they finally collide, giving astronomers an unprecedented prediction. They could then point every other telescope at that precise point in the sky, waiting to capture the kilonova flash and the birth of heavy elements in a coordinated, multi-messenger observation that would rewrite our textbooks. This is not just an upgrade, it is a transformation from catching random events to conducting a targeted symphony of discovery. While LISA listens to the ripples in space-time, a new generation of eyes will peer into the high-energy heart of these stellar corpses. The Advanced Telescope for High-Energy Astrophysics, known as Athena, is being designed as the most powerful X-ray observatory ever built. Its vision will be hundreds of times more sensitive than current X-ray telescopes, allowing it to see the faint, warm glow of neutron star accretion disks from the very edge of the observable universe. Where Chandra gives us a glimpse, Athena will provide a crystal-clear panorama. It will map the superheated gas swirling into these gravitational traps, measuring its composition, temperature, and velocity with breathtaking precision. This data will reveal the precise spin of the neutron star, the strength of its magnetic field, and even the properties of its solid crust. Athena could observe thousands of these distant X-ray binaries, turning individual curiosities into a vast population for statistical study. We will finally understand how common these cosmic vampires are, how they evolve over cosmic time, and what role they played in heating the early universe with their intense radiation. Completing this trifecta of future discovery is a survey of almost unimaginable scope. The Vera C. Rubin Observatory's legacy survey of space and time will not stare at one spot, but will scan the entire visible sky every few nights for 10 years. This relentless campaign will create a cosmic movie, capturing changes and transient events across the heavens. It will be a factory for discovery, identifying the fleeting optical counterparts to gamma-ray bursts and the afterglows of kilonovae by the thousands. When Lisa hears a gravitational wave chirp from a neutron star merger, the Rubin Observatory will be our fastest tool for scanning the vast area of sky and pinpointing the exact source of the light. Its immense database will also allow us to find neutron stars through a different method, by noticing the tiny, repetitive wobbles they induce in their companion stars as they orbit one another. This survey will find the needles in the cosmic haystack we did not even know were missing, providing the targets for Lisa and Athena to study in profound detail. Together, these missions represent a new era of synoptic astronomy, where we do not just look at the universe, we watch it, listen to it, and feel its vibrations all at once. These stellar corpses are more than just cosmic oddities. They are fundamental keys to the universe's grand narrative. From their birth in the first supernova to their silent endurance across billions of years, each fact reveals a piece of a larger puzzle. Their extreme density tests the limits of matter, their intense gravity warps the fabric of space, and their precise pulses act as clocks measuring the age of the cosmos. Every faint X-ray whisper, every gravitational ripple, is a direct message from the universe's violent youth, allowing us to probe eras no telescope can directly see. They are not merely distant objects, they are active participants in cosmic evolution, forging the heavy elements that built our world and seeding galaxies with the ingredients for future stars and planets. The 28 facts we have explored are not just a collection of trivia. They are chapters in an ongoing story of discovery, a testament to our relentless curiosity. We stand on a tiny world, gazing across an ocean of darkness, catching the faint echoes of these ancient powerhouses. It is a humbling reminder that we are connected to the cosmos in the most intimate way possible, built from the very atoms these stellar ghosts created long ago. So the next time you look up at the night sky, remember the invisible lighthouses spinning in the deep. Their story is our origin story. Keep watching, keep wondering, and follow the journey as we continue to unravel their secrets, one distant pulse at a time.